Welcome back, everyone. Today we're gonna cover a second topic of classification, and especially among them, we're gonna learn the new algorithm of classification, which is called a logistic regression. In the last time, we have learned two basic algorithm of classification, which is perceptron and SVM. And today, as the last topic of classification, we're going to learn the new algorithm of logistic regression. And I think you guys can be confused because in the algorithm, the name of logistic regression is included, so you guys can be confused. But interesting thing is, a logistic regression is indeed a classification algorithm, so please don't be confused. So when we think of the two algorithms that we have discussed last time, perceptron is kind of making use of sign of data. So if we have some data like this, we need to calculate the sign of omega tx. So whether by calculating the decision boundary, which is called exactly the same as omega tx is equal to 0, we can calculate the sign of theta of omega t times x, and based on that we can divide two classes. And in the case of SVM, we add additional terminology to use the maximum margin. That means by calculating the maximum margin, like from here to here, by calculating the maximum margin, our additional objective is to make the maximum margin. So margin is just nothing but the distance from the two closest data point. So from this decision boundary, the two closest data is like this. So by calculating the margin and maximizing the margin, we can implement a SVM algorithm. So, and finally, what we are gonna cover for today is logistic regression, which is using distance information of all data points. So please don't be confused. In the SVM, we just calculate a distance from two closest data. So we just measure the distance from these 2 points. But in the case of logistic regression, we calculate all the distance from these data. So that will be the idea of logistic regression. Then what's the meaning of using the distance for all data points? So let's see the motivation of logistic regression. So for that, suppose that we have very simple data points of only 2 points. For the circle one, we have class 1. And for the squared one, we have class -1. And let's say in this case, to divide these two data points, we can think of two cases of decision boundary. But when we think about the decision boundary, we intuitively we can think that the first case is the better case for measuring decision boundary, because it divides relatively the same distance for these 2 points. But in the case of second case, this decision boundary is more toward to the class 1. So for more general cases, we can think that the case 1 is more better decision boundary. So by keeping this in mind, our aim is just finding the decision boundary that divides two classes into the same distance, right? Otherwise, it will be toward into one classes. So it will not be the ideal case for the generalization. So idea is finding the optimal decision boundary that divides the minimum that divides two classes in the center. So for that, let's think about the very simple case that suppose we have only two data. So for that, in this case, let's assume that H1 is 5 and H2 is 5. And in this case, in the second case, H1 could be 3 and H2 could be 7. So based on that, let's find the optimal or ideal case to represent the center, to find the center of the decision boundary. So when we think about finding the summation of all the distance, then in this case the result will give the same result. But in the case of multiplication, this will give 25 and this will give 21. So based on that, we may use this value for we may use this value to be maximized for finding the center or the ideal case of decision boundary. And beyond this idea, there are the relation for this, and I guess you guys are already familiar with this formula, and we know that from this equation, the equality can be satisfied only if H1 is equal to H2, which is ideal case that we want to find decision boundary here. So for that, to maximize this value, our objective could be finding the multiplication of all the distance. So that is the basic idea of logistic regression. Our aim is just finding the maximized multiplication for all the distance. So in more general cases, anyway, the basic idea for logistic regression is finding the decision boundary that maximizes the multiplication for all the data point, all the distance of the data points. So that could be regarded as optimization, because our objective is finding the maximum distance, maximum values of the multiplication of all the distance. So for general cases, we have multiple data points, and our objective can be think of as maximizing the multiplication of all the data points. And this was the basic idea for this idea. So inequality of arithmetic and geometric means can be, the equality holds only if x1 and x2 and all the data points are the same. In other words, this optimization problem is just finding the decision boundary that is in the middle of two classes. So just exactly finding the middle points or middle line or middle hyperplane. So that would be the ideal case. So we have learned two algorithms of SBM and logistic regression that use distance between the data. In the case of SBM, we just measured only two closest data. So in this case, these 2 points are important. But in the case of logistic regression, we measure all the distance from the data. So that could be useful. But when we think about the case where the outlier exists, let's say these red points are outliers. That in the case of SBM, because we only measure the two closest data, the existence of outlier does not affect to the decision boundary. But in the case of logistic regression, as we measure the distance between the data points, this outlier may affect to the decision boundary, so the results can be biased to the class 1. So this is not a good case, right? So in order to solve this problem, we need to think about a new idea to overcome this limitation. So in order to avoid this limitation, that means to make the logistic regression to be more robust to the outliers, we're going to introduce a new function which is called a sigmoid function. I know that many of you guys are not familiar with this function, so let me introduce what the sigmoid function is. So the idea of logistic regression is finding the distance from the decision boundary to the data points. So by measuring the data points from here to here, the distance can be ranged from -infinity to infinity. So for that, here we're gonna link or squeeze these data points, the length of the distance of data points to 0 to 1. So for that, the distance from the distance of the data points will be squeezed to from 0 to 1. And for that, we're gonna use this sigmoid function. The sigmoid function has the form of 1 plus exponential minus g over 1. So when you put into -infinity to here, the data would be changed to a 0, right? When you put the -infinity to here, this goes to infinity, so 1 over infinity would be a 0. And when you put the 0 to this point, this would be plus 1 plus 1 over 1, so it would be 0.5. And when you put the infinity to here, this goes to 0, so the value would be the 1. So the value from the -infinity to infinity will be squeezed into from 0 to 1. So for that, we're gonna use this sigmoid function. And more specifically, for that, we're gonna squeeze the h, or omega transpose x. We're gonna squeeze the distance h. So when you put the when you put the omega transpose x instead of z, you're gonna have this format. And the one interesting one key point of this sigmoid function is kind of monotonic function. So that means it's kind of increasing function. So one of the reasons of using the sigmoid function for the logistic regression is we're gonna use some weight. We're gonna use some weight of the distance. So that means just measuring. When you just use the step function like this, similar to the perceptron, we're gonna just measuring the sign of omega transpose x. So if the sign is plus, then it will just give the same value of 1 regardless of the size of x. And in the case of minus, it will just give some 0 value regardless of the magnitude of the x. But for that, instead of using it, we're gonna use some weighted value for x. So if the x keeps increasing, then we're gonna use some weighted value for that. So that's why we want to use kind of this function. But when we just use write this, when we just use direct this linear function, if the outlier locate like here, this decision boundary will move forward to this because these distance would be really large. So instead of avoid it, we're gonna squeeze these value so that we can take the weighted value. So sigmoid function is this one is just the sigmoid function, or this is also called as a logistic function. So this is because why we call this algorithm as logistic regression, because we're gonna use this sigmoid function or logistic function. So logistic function always generates a value from 0 to 1, as we discussed earlier, and it crosses 0.5 at the origin, then flats out. So when you plot this sigmoid function, as we discussed earlier, the value would be like this. So when it goes to infinity, it will approach to 0.0, and when we keep increasing the x or g, this value would approach it to 1. So, but in the middle of this point, it's kind of similar to the linear function. So that's why we use this step function. So to implement this sigmoid function, we can import this Python code. So for that, you can just simply write the definition of the sigmoid function, and when you plot this figure, you can achieve this sigmoid function plot. So the benefit of mapping via the logistic function or sigmoid function is that the sigmoid function is monotonic, so it's just keep increasing function. So it will give the same or similar optimization solution. And also the sigmoid function is continuous and differentiable, so it is good to use gradient descent optimization. And mostly the sigmoid function can be understood as a probability or confidence that can be considered as probability. That means by measuring the sigmoid function, these values are just the value range from 0 to 1. So and when you calculate this sigmoid function, this value can be considered as the probability that can be classified as class number. So that means, let's say this is a decision boundary, and let's say we have some data points like this. And when you measure the distance, and by taking this as using sigmoid function, you're gonna calculate the value of minus transpose x over 1. And by taking this value, this will represent this data point can be classified. The value of this will represent the probability of this data point can be classified y is equal to 1 class. So that means, let's say this one is class 1 area and this one is class 0 area. And when you measure the h value, and by taking the sigmoid function, the value of this will represent the probability of this data point can be classified as class 1. So if this value is very large or high, then we can say that this data point can be is highly probable to be classified a class 1. But in the case of this point, the value would be a minus value, so that can be the logistic value of this would be really low. So that means this data point is not probable to be classified class 1. That means this data points can be classified class 0. So that's the key advantage of using sigmoid function. By using this sigmoid function, we can represent this data as a probability of to be classified class 0 or class 1. So we know that the probability can be ranged from 0 to 1. So the value can take this point. So probability that the level 0 is just nothing but the 1 minus p. That can be classified the class 1. So again, for a single data point x, y with parameters omega, the distance of the data points h omega x is can be calculated by substituting omega transpose x to sigmoid function, and this is nothing but the representing the probability of this data point would be classified class 1. And of course, for the probability that can be classified class 0 is just 1 minus hw, and that can be represented like this. And these two formula can be compactly written as just the multiplication of these values. And of course, for the generalization for m training data points, the likelihood or the probability function of the parameter is just nothing but the multiplication of all the probability. So the likelihood can be represented like this in mathematically. And from this likelihood, it will be easier to work on the log likelihood, because there are in this formula many multiplication is included. So if you change to this to log function, log likelihood, these values of the multiplication can be changed to summation, right? So let's use for convenience, let's use log likelihood instead of likelihood. And so the final form of this would be our objective function for that. So the logistic regression problem can be solved as a optimization problem to find the maximum value of these log likelihoods. So by doing so, we are just finding the middle plane of the data points that is robust to the outlier. So by using this, this one is the final form of the logistic regression. So the logistic regression problem is just nothing but the objective optimization problem with the objective function that is maximizing this log likelihood. And by keeping this in mind, from now on, let's implement this logistic regression algorithm using two methods. One is using just gradient descent, and the second one is scikit-learn, which is useful for most of machine learning algorithms. So for that, let's first implement this logistic regression using gradient descent. In order to use the gradient descent method, we need to find the derivative of it. So we need to calculate the gradient of the loss function, and for that we need to compute the partial derivative of the loss function with respect to the weight values. And if we go back to the definition of the loss function, we may calculate the partial derivative of with respect to each omega value. And for that, maybe we may calculate for each single data point with a single parameter for omega for the simplicity. And this one is nothing but the process of calculating the partial derivative. So when you calculate this process, maybe you may do it by yourself, and as a result, we can calculate we can obtain the final form of the partial derivative, which is just nothing but the y minus sigmoid x. So for m training data points for the generalization, we can obtain this format as like this. And the same as the other gradient descent optimization, as we calculated the partial derivative of the loss function, based on that we can calculate the gradient matrix, and based on that we can construct this update rule for the gradient descent for logistic regression. And here, please be careful that our objective is finding the maximum optimization, which is maximum of the multiplication of sigma omega transpose x. So by multiplying all the value, our objective is maximizing these value. So for that, we need to calculate this optimization problem. So for that, we need to calculate the minus gradient to find the maximum point. So please be careful that please remember this update rule for gradient descent for logistic regression. And let's implement this gradient descent optimization in Python. For that, let's first generate some random data set that is classified into these two classes. So for that, we just generate some random data of x0 and x1 using this omega and x. And from that, let's treat this this w and x as matrix. So let's convert this NumPy array into the matrix format, and let's label this data by using this equation. So this one is just measuring the probability of these x data, and if this one is larger than 0.5, then if this one is larger than 0.5, the data is labeled as C1, and if this one is smaller than 0.5, then the y will give the value for the force. So in that case, we're gonna take these data into C0. So for that, let's label this y value, and when you plot this data, you're gonna obtain this format where the C1 is represented as red and C0 is represented as blue. And by using these generated data, let's implement the gradient descent update rule using Python. So the idea is very simple, just measuring the h value. And the h value is just h omega is just returning the value of sigmoid function, taking this omega transpose x using taking this into the sigmoid function, which is just exactly the same as 1 plus exponential minus omega transpose x over 1. And as we discussed earlier, we can calculate the gradient of this loss function, which is nothing but x transpose y minus hwx. So let's calculate it. Let's first define the learning rate of alpha and omega, which is and let's initiate the W value, which is the size of 3 by 1. And for the iteration of for 1000 iterations, let's first define the gradient, which is minus x transpose y minus hw, and here we take this minus because we want to maximize this loss of this L omega function. And if we update this value, then we can obtain the W value. And when you plot this on this plot data, we can see that the logistic regression decision boundary for the logistic regression appropriately divide these two data into two classes of C0 and C1. And secondly, let's implement this logistic regression using scikit-learn. As we discussed earlier, scikit-learn is very useful for various machine learning algorithms. So similar to other algorithm, logistic regression using scikit-learn is very simple. So you may just import the linear model from scikit-learn, and from the linear model, let's use just logistic regression. And here you don't need to set the solver, but for the convenience, let's just see the solver like this. And based on the defined model, if you just use this fit function from the x data and the labeled y, that is all. Just using this command, you can automatically find the logistic regression function for the weighted value, and the value will be saved as like CLF.intercept, which is just nothing but the omega 0, and CLF.coefficient 0,0 will save the omega 1, and CLF.coefficient 0.1 will save the value of omega 2. So by using these one sentence command, you can automatically obtain the trained weight value, and based on that, you can just when you plot these data, you can see that the logistic regression model appropriately divide these data into two classes of C0 and C1. And finally, let's expand this idea to multi-class classification. So far we have discussed only a binary classification where we have only two cases, like class 0 and class 1. But here, let's think about a multi-class. So the data can have like more than two. So the data can have more than two classes. So, but you don't need to worry about that. A generalization to more than two classes is straightforward. So the idea is whether you may think one versus all, or one versus rest, or one versus one. So let's say we have data points like this. So we have three classes. To take this, the first algorithm is just taking the one versus all. So you may classify these one data and the rest of it. So by using this, you can find the decision boundary for this line. And for the secondly, for this data and the rest of it, so for that you may find the second decision boundary. And lastly, you may find this data and the rest of it. So by using this, you may find the final decision boundary. So by using that, you can divide these data into three classes. That is the algorithm for the second case, for the first case, and for the second case is also the same. This one is just 1 versus 1. So here we may first ignore this data set, and so by ignoring this, you may find the first decision boundary. And the second case is just ignoring these data. So you may find the decision boundary that can divide this data and this data. And the third case is ignoring this data. So by using this, you may find the decision boundary that can divide this one. They can divide this one and this one. So by doing so, by keep doing this, you can find this decision boundary. So that is the expansion of using a binary classification into multi-class classification. Yeah, so that's it for today's lecture. So in summary, we have learned the final algorithm of logistic regression. So as we discussed earlier, a logistic regression is kind of a classification algorithm. So don't be confused don't be confused to be a regression algorithm because the name includes the regression terminology. It's just nothing but the classification algorithm. So the idea of logistic regression is using all the distance information of all data points. So instead of just measuring the margin or the two closest data, we used all the data points and all the distance information to decide decision variable. And here, and also, in order to make this logistic regression to be more robust to outliers, we introduce a new function which is called the sigmoid function or logistic function. And by using this sigmoid function, we finalized this objective function that is by finding the and by using the maximum point of this loss function, our model can find the middle point of the data among these data. So yeah, so that's it for today's lecture, and thanks for your listening.